Hello everyone, so my name is Cassandra and I've been on the bee health assurance team now for 3 years. I mostly worked with Rasul in the laboratory. Actually, we're going to discuss one of the studies we did or the pilot projects we did, but today I'm going to talk about the use of oxalic acid for Varroa treatment, kind of an update on 2 studies we've done and then kind of what we're looking for in the future. So the background, I think that my general background has been covered multiple times now, so I'll kind of whiz through that, but just a general overview of Varroa, talk about the history of synthetic miticides in Alberta, and then talk about alternative treatments focusing on oxalic acid. And then I'm going to get into oxalic acid in Alberta. And in 2017, we did a pilot project or a little study on oxalic acid strips in the hive versus shop towel. And then in 2018, we did oxalic acid vaporization project. And then lastly, I'll talk about conclusions and just future directions. So this is a very large picture of a Varroa mite. It's quite gross. So it was introduced into Canada in 1989, and then by 2002, it had pretty much spread across the country. So we know that Varroas, they're pretty lethal, and they can kill a colony in 1 to 3 years if they're left untreated. Sam did mention this before, but Varroa do feed on the fat body, and that has pretty large implications for overall bee health, but also winter bees that rely on that fat body to make it through our really long and cold winters. And again, we know that Varroa also are vectors for transferring viruses. So just a brief history of the synthetic miticides that we've used. So first, in the 1990s, we had Apistan, but around 2002, we started seeing resistance in the mite populations to Apistan, so we introduced check mite, which is Coumaphos, and that was around from about 2002 to 2007. Again, saw the same thing. We saw resistance there, and then now we have Apivar, and that was introduced in 2008, and we've pretty much been using that exclusively for about 12 years now. And Sam had mentioned in her talk that Apivar is still effective in Alberta, but it's not as effective as it used to be. And this is really important for us, and especially for monitoring, because there's other places around the world that have developed resistance to Apivar. And then Sam also talked about Baverol as well, so you saw that in her presentation. Same chemical family as Apistan, and there was quite a lot of variation in its efficacy, so pretty much depending on different operations, so it wasn't quite effective. And then she also touched on the fact that we don't really have another option for the future. But as you can see here, and pretty much why we're all here talking about integrated pest management, we essentially exhaust one synthetic chemical until we can no longer use it, and then we rely on something else to come in. Another important aspect of the chemicals, the synthetic chemicals that we use, is that they do leave chemical residues in the colony. And so I like to personally think about, well, here you have a frame of new comb and then older comb, and I like to think of the wax kind of like a duster. So essentially it just collects all of the things that the bees bring in from the field and also the stuff that we put in the colonies. And we know for a fact that the wax does collect a lot of agrochemicals. So Mullen et al. 2010 found 121 different agrochemicals in colonies throughout North America. And kind of bringing that more home, Apistan and check mite specifically have a half-life of 5 years. So kind of touching on what Sam said, so if you were to put, let's say, Apistan in your colony once, and you're like, nah, I don't want to use this anymore. If you came back in a couple years and you tested your comb, you would probably still be able to find that chemical in your comb. You're probably wondering, why does this matter? Well, Sam, again, and a lot of people actually touched on this before, when you have residues in the colony or you leave your strips in for too long, you're essentially exposing the mites to a very low dose of the chemical, and that helps expedite resistance or create a tolerance for the mites. So I have an analogy. I've been waiting all day to do this, and I'm hoping I can pull it off. Who has seen The Princess Bride? Can I have a show of hands? Woo! Honestly, if no one had seen it, I was just going to move on. But anyway, okay, so I hope everyone can remember what this scene is. Here we have Wesley in the black. He's the hero. Then we have Princess Buttercup, and she's being potentially rescued by Wesley. And then we have Vicini, who's a Sicilian criminal. And right now, well, Vicini really prides himself on his intellect. And so they're having a battle of wits. And Wesley suggests that he poisons 1 goblet of wine with iocane powder. And Vicini agrees, so he turns his back, puts the iocane powder in both goblets, and then comes back, and then you have 5 minutes of Vicini trying to deliberate which wine glass has the poison. Then they both drink. Within 30 seconds, what happens? Vicini dies. But Wesley is left unscathed. And why is that? It's because for the last 2 years, he's been exposing himself to iocane powder in low doses, and he's built up a tolerance. And so essentially, Wesley is a Varroa mite. Thank you. Thank you. I was honestly laughing so hard at my desk. I was like, oh, this is so good. And I'm really happy you liked it. Sweet. So, knowing that and knowing kind of how we have used synthetic chemicals in the past and moving forward, we definitely need alternatives. And Sam also mentioned this, one of her last slides is like, while APVAR is still effective, let's keep it that way. Here's a picture of Sam promoting integrated pest management from the late 2000s. You see your little toolbox there. So what we suggest doing is adding in soft chemicals like formic acid, oxalic, thymol, etc., that have different modes of action to the chemicals, the synthetic chemicals that we use. And these are essential for the IPM. So our goal is to prevent the development of resistance in these synthetic chemicals that work really well when they work, from the overuse or misuse of these pesticides. So I'm going to talk about oxalic acid. Grab a drink of water. There was ice. We're okay. Okay. So it's naturally occurring carboxylic acid found in nature. Sweet. So of course, everyone probably recognizes the picture at the bottom. What is that? That's rhubarb. Yes, we can eat the stalks, can't eat the leaves, and that's because they are full of oxalic acid and poisonous to us. And please do not put this in your colony. We have no idea what the implications are. Because oxalic acid is found in nature, there's actually a very low risk of contamination in honeybee products. And it also rapidly degrades in colonies, which is the opposite of pretty much of the synthetic chemicals, and that results in that like lower selection pressure. So for oxalic acid in killing Varroa mites, the mode of action is actually unknown, but we do know that direct contact is required, and it's possible that the Varroa might just have a sensitivity to the low acid or the low pH. So there are 3 main methods of application for oxalic acid. One is the drip trickle method, and that is where oxalic acid is dissolved in a sugar solution, and 5 mils is dribbled between the frames and the colony, just all over the bees, up to 50 mils per hive. The next one is the sublimation vaporization method. So oxalic acid crystals are vaporized at 157 degrees Celsius, but it's super, super important to remember that at 189.5 degrees, oxalic acid actually degrades into formic acid, carbon dioxide, carbon monoxide, and water. So that's definitely something that you need to consider when you're vaporizing. Oh no. This one? Hello? Okay, I can lean forward, it's cool. Okay, last one is the spray method, and it is not registered in Canada. This one is again where you dissolve oxalic acid in sugar solution, and then you have to spray it on every frame of the bee. Bees, not only is this time intensive, but it's quite invasive for the bees as well. So oxalic acid methods have been tested all over the world, and it's been about a decade, I think, since we've tested it in Alberta. So we want to kind of figure out what oxalic acid is like with the new products on the market. So we do know that oxalic acid is most effective on broodless colonies because oxalic acid cannot penetrate the cell capping, unlike formic acid. So we're going to go into the 2017 oxalic acid study that we did. So this is strips versus shop towel. So there's a paper that came out in 2016 by Maggie et al. And what they had done was they dissolved oxalic acid in glycerin and then applied it to strips. So this was kind of like the first time oxalic acid was put in a colony for longer periods of time, kind of like the synthetic strip formation. So you could have it in there over 1 or 2 brood cycles to get those mites. And then Randy Oliver did something similar, but he used blue shop towel, which I'm pretty sure everyone in the room knows about. So our objective was to compare the efficacy of the cardboard strip method as described by Maggie et al. And then the blue shop towel method described by Randy Oliver under Alberta conditions, and this was done in the fall of 2017. So disclaimer, this method is not yet registered as an application method in Canada. So for our methods, so we had 21 colonies in total, so 8 colonies for the cardboard strip, 7 for the blue shop towel, and 6 as control. And this experiment was done over 2 months, so In October, you can see there's the blue calendar days. Those were just when we put sticky boards under the hive to get kind of like the natural mite drop before we treated. We treated on the 10th, and then on the 24th, they had to add another treatment of the blue shop towel because I think the bees completely ate it, and then they had to replace it. And then the experiment was finished on November 14. So during this time, samples were taken 7 times, so before and after, and then 5 times throughout the experiment. We also placed sticky boards in the bottom of the colonies and replaced them every 1, 2, 3, 5, and 7 days after treatment. And at the end of the experiment, we finished the treatment with APVAR so we could get the total number of mites in the colony. And here were our results. So interesting to say the least. So on this graph we have, on the y-axis, we have the average mite drop, and on the x-axis we have the period. So this is from the sticky traps. I'll draw your attention to the black line here, which is the strip, and you can see it does what we want it to do. You know, we put it in there, you get an increase in mite drop, and then it kind of trails off over time. But then you look at the shop towel, and it's very perplexing. You're like, why is it no different than the control? Well, what they found was that the blue shop towel was working, but most of the mites were falling onto the shop towel instead of falling onto the sticky board, so we couldn't count them. So this is when you look at the before and after the treatments. Again, you have the mean abundance of mites on the y-axis, and then before and after on the x, and then that red dotted line is the economic threshold. And you can see here that both of the methods were effective at reducing the mites actually below the economic threshold. So the cardboard strip reduced the mite population by 95%, and then the shop towel reduced the mite population by 90%. Okay. So the second one we did was in 2018, and it looked at oxalic acid pilot project for vaporizers. We gave all the bees small vapes, and then, I'm just kidding, we used these machines here. So the objective of our study was to compare 3 different models of oxalic acid vaporizers, and we wanted to look at mite mortality, but we also wanted to look at how, like, the usability of these devices as well. So we looked at the ProVap, the Varroa cannon, and the Varroa blaster. I was freezing this whole time. And this was done over November and December. So we had 21 colonies in total in this experiment. We had 5 apiaries on site, and the average mite infestation was 8%. So 7 colonies went for the ProVap, 7 for the Varroa cannon, and 7 for the blaster. Again, we did very similar things to the study before. This is in November, so those blue calendar dates, again, that's when we put those sticky boards in to get the natural mite drop, and then we started treating on the orange. And we treated once a week for 4 weeks. It was not perfectly aligned because we had some weather delays, and so we had to bump it back. But same thing, we treated, before we did any oxalic acid treatment, we would take a sample. We also had sticky boards in there, so we would exchange those. We'd treat, and then we'd put a sticky board in, we'd come back and we'd change them every 1, 2, 3, 5, and 7 days after treatment. And then, of course, at the end, we finish with APVAR to get the total mite population. All right, so here we have a graph with mean abundance of mites in percentages, mites per 100 bees on the Y, and then before and after. That red line again is the economic threshold, and looks good. All the vaporizers reduce the mite populations over our study period below the economic threshold. And more specifically, the ProVap reduced Varroa mite levels 98%, the Varroa blaster reduced Varroa mite 94%, and Varroa cannon reduced 96%. But if you look at them individually, so I'm going to draw your attention to this black line here, which you can't really tell it's black, probably from over there, but it has a little square. That's the ProVap. So we treated once, and it only took 1 time to reduce the mite populations below the economic threshold. This was the same for the Varroa cannon, but it actually took 3 treatments in order to reduce the mite levels that were treated by the Varroa blaster. So looking at the usability of these devices, so the ProVap, very short warm-up time, but it did depend on the ambient temperature. That goes for all the devices, really. The application time was about 20 seconds per hive, and this was nice because you could apply an exact amount of oxalic acid per hive because there's a little scoop and you can measure it. I think one of probably the downfalls is that it only treats one hive per oxalic acid load, so every time you have to go back in and reload it. The ProVap only requires a generator for operation, and we found that one person could easily go out and do it by themselves. For the Varroa cannon and blaster, they had very similar things. So the warm-up time was about 5 to 15 minutes, depending on the temperature. They both required a generator and an air compressor for operation. We found that they treat approximately 4 colonies per oxalic load, so 10 grams per load. We applied the cannon and the blaster for about 10 seconds per colony. The nice thing about the Varroa cannon was that it actually had a trigger mechanism, so you could load the cannon and then make sure that you were actually in the entrance of the hive before you release the oxalic acid, which was really great. The blaster didn't have that, and so sometimes we weren't perfectly aligned with the colony entrance, and you started spewing oxalic acid and also wasting money, I guess technically, before we got in the colony. And we also found that it was really nice to have 2 people for operation, so one person holding the device and then the other person loading the oxalic acid for the cannon and Varroa blaster. Okay, so as you can see, we have some promising results. I just want to draw the attention to the fact that we did treat in late fall, and if you're treating at that time, it's probably a little bit too late for your colonies, as Sam mentioned in her talk. But the strip versus strop towel, they reduced the mites below the economic threshold, but do not forget that this is not registered for use, so please do not start using this in your hive. So, and the vaporizers, all 3 devices reduced mite levels below the economic threshold within our study period. But obviously moving forward, we need to do a little bit more research, talking about effective dose, timing of treatment, if there's any residues or any negative effects on bees or larvae, etc. And in the future, we definitely want to look into a mid-season treatment. So I know Sam mentioned with that graph, trying to hit the bees a little bit before that graph starts growing exponentially, so you can your winter bees are healthier. Yeah. So thank you.